Good evening, everyone. I hope you're doing great, that you're feeling like the midterm is something that you're ready for and that you're studying as best you can. Remember to look at all your old notes, look at your warm-ups. If there were challenging problems that we did, look at those. Those are probably something that's worth reacquainting yourself with. And then all the homeworks that we've done and passed back to you graded, those are good places to start, along with the midterm review packet. Hey, there was a problem, a front and back, that I gave out at the last class meeting. Practice for midterm, it was called. And as promised, I'm going to make a short video that goes over these two problems. And let's get started on that now. The first thing I'd like to do is just show you the entire assignment so that those of you that looking at my solutions is all you need, you can go with that. I think reading what I wrote is useful to you, so do so. Now I'd like to just quickly look at the problems, and I'm going to go as fast as I can. The first problem says that a dart gun is shot straight upward and emerges from the gun traveling at 45 meters per second in the positive direction. So that's upward at 45 meters per second. We know that I've asked you to use negative 10 meters per second squared for acceleration. And I just want to remind you what that means. Remember that acceleration is the change in velocity over time. And so 10 meters per second squared, negative 10 meters per second squared, means that the velocity changes by 10 meters per second every second. So you could do this in your head, really, if you thought about it this way. At 0 seconds, it's going 45 meters upward. After 1 second, it's going to be going 10 less than that, or 35 meters per second upward. Well, this goes pretty fast. After 2 seconds, after 3 seconds, after 2, it's going to be going positive 25, right? Because it's losing 10 every second. 45 minus 10 is 35. 35 minus 10 is 25, and so on. After 4 seconds, it'll have lost another 10, so it'll be 5 meters per second is its velocity. After 5 seconds, it's actually gone negative, right? It's gone from 5 minus 10 would be negative 5. And so I've gone far enough because the question that was posed, what is the minimum amount of time before the dart's velocity will be negative? Well, it went negative right after the midpoint between 5 and 4 seconds. So after 4.5 seconds is really a good way to look at that. The next problem involves a car starting from rest and accelerating to 20 in 5 seconds. What's the slope of the graph? Well, again, slope is rise over run. And so the rise is how much change in the y-axis quantity there is, and the run is how much change in the x-axis quantity there is. The rise will equal 20 minus 0, or 20 meters per second, right? Because that's what velocity is measured in. And the run is in seconds, and it's 5 seconds. Final 5 minus initial 0. 5 minus 0 is 5. Now, of course, 20 divided by 5 is 4. But before you walk away, look at the unit. The change in the y-axis quantity, 20, was measured in meters per second. And then you divided that by the change in the x-axis quantity, which is measured in seconds. That's meters per second per second. Holy smokes, Batman. That's meters per second squared. So what the slope of the graph numerically is 4 meters per second squared, but this tells us the acceleration. Is the slope of every graph acceleration? Well, no. This is a velocity time graph, and so its slope is the change in meters per second per second, which is acceleration, but the slope of an xt graph we've talked about is velocity. Okay, so what about the area under the curve? Well, the curve is the line. In this case, it's not curved, but we refer to all graphs as curves technically because many are curved. Anyway, the slope, the area under the curve is the area of this triangle that I've just shaded. And of course, the area of a triangle is 1/2 the base times the height of the triangle. That's just a formula from geometry. Let's go ahead and put in our values. Our base has a size of 5 seconds. And the height, of course, is 20 meters per second. Doing the math, 5 times 20, of course, is 100, and half of 100 is 50. But again, don't walk away without analyzing the units a little bit. Seconds, all by itself, is really like seconds on top of 1, seconds over 1. Well, that makes the seconds here on top. And these seconds are on the bottom. And I'm not sure you remember multiplying fractions, but when you multiply two fractions, there's something called cross-canceling that can be done if the diagonal crosses are the same thing. So the seconds on top cancel the seconds on the bottom, leaving meters. And so that is actually the unit of the area. It's 50 meters. And that gives the displacement of the object. Now, the last part of this question, it really should have been called like question 2A, B, and C, really, because all these parts relate to this graph up here. But I ask you to draw the xt, the distance time graph, in meters as a function of seconds, the acceleration in meters per second squared as a function of seconds time. What would this behavior, this constant change from 0 to 20 meters per second, that's accelerating constantly from 0 to 20 meters per second, what does that look like? Well, let's, for God's sake, let's look at the AT graph first. The AT graph, the rate of acceleration is 4 the whole time. I mean, the slope between these 2 points is the same as the slope between these two. Then the slope is not changing. The slope is constant. And that means the acceleration is constant. So I'm really looking for you to have drawn a horizontal line of 0 slope at a value of 4 meters per second squared. And lastly, when you're accelerating, your distance, if it were flat, that would mean you're not moving. If it was a straight line that's diagonal, that would mean you have a constant velocity that's not 0. But here you have a constant acceleration. Your velocity is changing. So you're going to need to make sure that that's a curve. In this case, concave up because it's increasing its velocity. I suppose if it was decelerating, it'd be concave down. But we're not going to fuss with that. Let's keep going. This problem we talked about in third period really quickly at the end of the period. This is one of those reminders that when it asks you to find average speed, you are not going to make a V naught, VA, XT. You're not going to do an acceleration list. There's only one equation for average speed. Average speed is simply the total distance traveled divided by the total time. And so we have a distance of 40. If you read the problem, I'm trying to make this short, so I'm not going to read it to you, but the numbers tell us that the ball rolled 40 meters in 10 seconds. 40 over 10 is 4, and the unit is meters per second. Let's look at the back quickly. These are ranking tasks. A lot of evidence shows that kids think differently and in a more meaningful way when they're asked to evaluate things and rank them. So here's the question. The first one, horizontally launched trucks, toy trucks, time in air, number 1. It says a toy truck is launched horizontally from a table of height h, and in case A, the toy truck leaves the table with a speed v. In case B, the toy truck leaves the same table, height h, with a speed 2v. So the difference is only that this one is going twice as fast horizontally to begin with. Now, presumably the trucks fall to the ground, and you're asked to evaluate the student's statement. The student said, the faster you go, the less time it takes to get there. And that's certainly true if you're going to Los Angeles or San Jose in a car. The faster you drive, the less time it takes to get there. But here's the second statement the student makes, and there's a problem with this statement. The student says, you go faster, you get there quicker, so truck in case A is going to take longer to hit the ground. It's in the air for longer. Well, that's false. And I just want to keep reiterating that what happens in the X and what happens in the Y dimensions, the vertical dimension, in this case H is kind of like the Y displacement. And so what's going on vertically and what's going on horizontally are totally independent of each other. They don't affect each other. So what does determine the time that these trucks take to hit the floor? Well, it's a vertical issue. It really has to do with the acceleration due to gravity and the height of the table. We could make a vertical list. I'll do that super quick. And remind you that when things are horizontally projected, going perfectly sideways, horizontally to begin with, it's as if you dropped them in terms of their vertical motion. There is no vertical initial velocity at the instant it leaves the table. So our list looks like initial velocity 0, final y velocity. I'm not sure I can know that or care. Let's leave that for now as not applicable. Acceleration due to gravity, negative 9.8. The distance vertically it's displaced, y, is h. I don't know what it is, but I know it's the same for both of them, so I wrote down h. And time is what I'm looking for. So recall that the equation we typically go to when the final y velocity is not available or missing is this third equation of kinematics. Vertical displacement equals initial vertical velocity times time plus 1/2 at squared. If I've done this once, I've done it 1,000 times. This initial velocity being 0 makes this whole term 0, and this simplifies to y equals 1/2 at squared. A little algebra, doubling both sides, multiply by 2, divide by a, take the square root, yields that the time to fall down to the floor is 2 times the vertical displacement, in this case h, divided by a square rooted. Well, this is a constant. This is a constant for both trucks. Only thing that only thing that matters is the vertical displacement, and it's the same also. So this whole quantity is the same for both trucks, and so both trucks take the same time to hit the ground. 2 exclamation points because it's such an important point. I'm kidding. All right, last question, and we'll edit this video and send it along. The rifles in the figures are being fired horizontally, again, perfectly sideways, straight outward off platforms. The bullets fired from the rifles are all identical bullets. Not that that matters. We know that all things fall at the same rate. But let's just say the bullets are the same mass and same shape and same, everything. But the rifles propel the bullets at different speeds. This one's going very fast, 1,200. This one's going fast too, 500. This one's going faster than that, 800. This one's also going 800. Okay, so the speeds are different. And it says the speed of each bullet and the height of the platforms are given 20, 40, 40, and 30 are the platform heights. All the bullets miss their targets and hit the ground. So each bullet is going to be allowed to fall long enough to hit the ground. Rank the time that it takes the bullets to reach the ground. Well, again, I'm not going to go through the whole list and the whole solving it for t after choosing the equation 3 up here, but it comes down to the vertical height, the acceleration of gravity, and this factor of 2 under the square root. Again, this is a constant. It never changes. For all the bullets, it's the same, 2. This is negative 9.8. It doesn't change. So really, the bigger y is, the bigger time is. That's all that matters. So the rankings, these are the 2 largest heights, and they're the same. So B and C take the longest time. They wanted us to rank them from greatest time to least time. So I put the big times first. 40 and 40 yield equal times. The 30 bullet D, platform D, is going to be the second or the third place finisher. Bullet in scenario D, falling from less height, is going to get there a little quicker, so a little less time. And then the least time is bullet platform scenario A. Again, if you stayed in there, hung in there with me that long, take a quick photo if you need to of the whole sheet. And here's the front side one more time. And again, good luck, and I'll see you around the way.